Someone mistakenly put a lovely couch out to the curb on garbage day, and you decide to take it back to your apartment. You push on the 110 kilogram couch with a force of 410 newtons directed at 35 degrees below horizontal. The couch does not move. So, first we are going to draw the free body diagram. I have a force of 410 newtons. It's directed at 35 degrees below the horizontal. So here's the horizontal, and this is an angle of 35 degrees. It's below the horizontal. This, let's call it the force of the push, is equal to 410 newtons. Then, all the forces I have on my free body diagram, except for the force of gravity, come from something that is touching the couch. You are touching the couch and pushing on it. We also have the force of gravity acting downwards. This force of gravity is equal to mass times little g. The mass of the couch is 110 kilograms. Little g is 9.8 meters per second squared, and that gives me 1,078 newtons. And then the ground is touching the couch. The ground exerts a normal force, which is perpendicular to the surface of contact, and that is acting upwards. Because the couch does not move, we know that there must be a frictional force opposing the motion. Because the couch does not move, this is static friction. Now, we can break this 410 Newton force down into horizontal and vertical components. So I have my 410 Newton force is going to form the hypotenuse of this right triangle. This is the horizontal component. This angle is 35 degrees. This is 410 newtons times cosine of 35 degrees, and that is 335.9 newtons. This side of the triangle is opposite to the 35 degree angle, so this side is 410 newtons times sine of 35 degrees, and that is 235.2 newtons. Now, at this point, I'm going to draw a new free body diagram. You could put these components on your original free body diagram instead of drawing a new one. And we have the normal force acting upwards. We have the force of gravity, which is 1,078 newtons acting downwards. We have this force of static friction, and we have the horizontal component of the force of the push, which is 335.9 newtons, and then we have this component, which is acting downwards, and that's 235.2 newtons. And then, since this is the dynamic section, we should be using Newton's second law, and we can use Newton's second law in the x direction and also in the y direction. In this case, since the couch is not moving, the acceleration in the x direction is equal to 0, and the acceleration in the y direction is also equal to 0. So because the acceleration in the x direction is equal to 0, the sum of the forces in the x direction is equal to 0, and because the acceleration in the y direction is equal to 0, the sum of the forces in the y direction is equal to 0. If the sum of the forces in the x direction is equal to 0, that means the leftward forces have to be equal to the rightward forces. So if you say this way is positive, then you have positive 335.9 minus the force of static friction is equal to 0, or you can just say 335.9 is equal to the force of static friction. Notice that we did not use our equation from page 57 here, because this, where you take the coefficient of static friction and multiply it by the normal force, gives you the maximum value for the force of static friction. So we know that the force of friction has to be less than the coefficient times the normal force, but that doesn't tell us what the force of static friction is. So we just find that from summing up the forces in the x direction. I can also sum up the forces in the y direction to get the normal force. I can say that up is positive, and then I would have the normal force minus 235.2 minus 1078 is equal to 0. Or I can just say if the sum of the forces is equal to 0, then the upward forces are equal to the downward forces. So I have the normal force is equal to 235.2 plus 1078. And that gives me, for the normal force, 1,313 newtons, where this N is for the normal force and this N is for the units newtons. Okay, so at this point I could be done with the problem. I know the force of static friction, maybe I just want to rewrite that. Force of static friction is equal to 335.9. We can leave it as 335.9, or we can round it to 336. Because the couch is not moving, there's no kinematics to do in that problem, so we found all of the unknown forces. But if you check the answer that they give you in the back of the book, what they give you is actually the coefficient of static friction. And so we cannot find exactly what the coefficient of static friction is, but we know that it has to be that the force of static friction has to be great enough to prevent the couch from moving. So we can use the equation that they give us on page 57, but instead of writing it this way, I prefer to write it as the maximum value for the force of static friction is equal to the coefficient of static friction times the normal force. Or you can take what we have here and say this force of friction, that would be static friction, that must be less than or equal to the coefficient of static friction. This force of contact here, that is the normal force. So that would be less than or equal to the coefficient of static friction times the normal force. I know what the force of static friction is, so I have 335.9 is less than or equal to the coefficient of static friction times the normal force, which is 1,313. Then I can divide both sides by 1,313. And that gives me 0.256. So from this I can say the coefficient of static friction must be greater than or equal to 0.256, because when you push on the couch with this force, the couch does not move. The vertical component of this force makes the normal force larger, so if you only pushed horizontally, the normal force would just be equal to 1,078. And the force of static friction is whatever it has to be to balance out the horizontal component of the push. And if we put units in here, this would be newtons over newtons, and that would cancel out, so there are no units for the coefficient of friction.